Okay, hello, physics fans, fanatics, fundamentalists. Here we go. We are going to do our Unit 3 review on all things magnets and magnetism. This is over chapters 28 through 30 in your textbook. So we're going to be talking about magnetic fields, magnetic forces, and magnetic induction from Faraday's law, and a bit of inductors and RL circuit stuff at the end. Okay, so for your test, I've given you this formula sheet, which is, I think you'll agree, a real masterpiece of graphic design. Very busy, a lot of stuff on this sheet, but I do encourage you to acquaint yourself with all of the different dongles on there to, be able to use them in problems. So that's what we're going to try to do in this video. Try to give a quick overview of all the stuff on here so that you can, after watching this video, go ahead and try your review test and see how you do. Okay, so magnetic forces and magnetic fields. In chapter 28, we talk about how magnetic forces are a little weird because they follow the right-hand rule. V and B, V is your index finger, B is your middle finger. In fact, we should instead see this as the direction of current, because Q times V gives you the direction of the current. Remember, if we have a negative charge here, we could point the other way. Okay, so we have current is our finger. The magnetic field that's acting on the current is our middle finger, and then our thumb is the direction of the force. And the thing to keep in mind, the current and the magnetic field do not have to be perpendicular. In fact, you get the biggest force if they are perpendicular. If they're parallel, because this is a cross product, that force would go down to zero. But in any other angle other than just where current and magnetic field are in the same direction, you do get a force. It's depending on this, because of this is a cross product, it's dependent on the sign of the angle between V and B, or I and B. But in any case, this force is perpendicular, so it's not causing the particles to accelerate, it's causing their direction to change. And so that led us to charged particles going around in a circle, or if they had been moving, this is the case where the magnetic field and the direction of the velocity are perpendicular to one another. If they're not, you get a helix, and only the part of the velocity that's perpendicular to the magnetic field will be changed. Now, this was our first right-hand rule. Our second right-hand rule had to do with the Biot-Savart law. And this said, you put your thumb in the direction of the current, then so the current is in one place, that's where you put your thumb. Then the palm of your hand is in the direction pointing from the current out towards the point of interest where you want to look at the magnetic field. Then your fingers on your right hand curl over, and they are going to be pointing in the direction of the field. So in the case, for instance, of a long straight wire, you have your magnetic field that's essentially going around at each point it has a direction, which you can figure out by curling your fingers around. But if you go around and draw a field line, it's going to be making a loop. And so our magnetic dipole is our model where we have a loop of current like this. So that's our I. And if you loop your fingers around, the fingers of your right hand around that loop, then your thumb is pointing up in the direction that the magnetic moment is pointing. And this also happens to be the direction that the magnetic field on the top is pointing, and it would be pointing in the other way on the bottom. And then around here, the magnetic field lines make loops like this. Okay, so that's our model. Our simplest model for a permanent magnet is just the idea of like a little loop of current. Okay, so let's try to think our way through some of these. Most of the problems I'm going to go over today are just problems we've already done. So I'm warning you about that, but I do think it's reasonable for us to not introduce new stuff today. We're just going to review where have we been. So for instance, if I have two parallel wires in the XY plane, each 2 meters long, separated from one another by 3 meters. Okay, so let me draw that situation. You've got your I1 and I2. They are 3 meters apart. And we're considering this distance, this L, to be 2 meters. They each carry 4 amps of current in the plus X direction. What magnetic force does each wire cause on the other? Does this force cause them to be pulled together or pushed apart? Now, I've said in previous videos that if you have two parallel currents, both going the same way, they will pull each other together. But let's make sure we understand it because it is important in terms of the right-hand rule. So let's the force will be the same on each. One will pull down, the other one will get pulled up because they're being pulled towards each other. But if we want to understand why, we can pick out one of those forces to think about. So here's wire 1, there's wire 2. The thing is, the way to think about this is that wire 1 has a magnetic field going around it. That magnetic field pulls on wire 2, which feels a force. Okay? So, if we want to find the force on wire 2, for instance, we could first find the magnetic field from 1 at the position of 2. So this is that's determining R. So that B from wire 1 would be mu naught times I1 over 2 pi, and then the R would be how far apart they are. And then for the force, so and then it's important to try to figure out what direction is that field. So at the position of 2, that B1 is going to be going into the page. And you can figure that out by putting your thumb in the direction of current 1, putting your hand down towards the wire 2, and then curling your fingers around in the direction of wire 2. Okay, and then the force is going to be related to the current times the length times the magnetic field. So that force that's acting on this wire 2 is going to depend on the current of wire 2, the length of that, so that would be 2 meters here, and then it would be mu naught, and well, let me just write it as times B1. Okay, so that just comes from this. And that, if we put in the magnetic field from that wire 1 in there, we would get I2 times L times mu naught I1 over 2 pi R. Okay, and then this, it turns out, is going to be the same for each case. It's just that the forces are going to be in opposite directions. And how do I find out what directions the force is? I got to use my right hand rule. So to find the direction of the force on wire 2, I've got to put my index finger in the direction of the current in wire 2, my middle finger in the direction of the magnetic field that's pulling on that current, and then my thumb is pointing up as it should be. Okay, and then you stick all those numbers in. Keep in mind, mu naught is just a number. Length, we've got that r, that distance between the two wires we have, and we have the currents, and you can stick all of those in and get 1.6 times 10 to the minus 6 newtons. Okay, now here's another type of problem that you can get. We have a magnetic force that acts on particles, but that's not the only force that could act on a particle. We also have the electric force, so that's due to the electric field, and we have gravitational force, and that's due to the gravitational field. Now, the gravitational force is always pointing in the same direction as the gravitational field because mass is always positive. The electrical forces are always pointing in the same direction as the electrical field for a positive charge, or opposite the direction of the electric field for a negative charge. Now let's take a look here. An electric field of 1.5 kilovolts per meter. So that's the size of E. 1.5 times 10 to the third volts per meter. That's the same as as newtons per coulomb. Pointing east. Okay, E for electric field, E is also for east. And a perpendicular magnetic field of 0.4 Tesla pointing north. So here's B pointing north. Act on a moving proton to produce no net force. What is the proton's velocity? Include both speed and direction. Okay, so what I want you to appreciate is that if we drew a proton here, the electric field is pointing to the east, then my electrical force would be pulling also to the east. So there's the direction of the force is the same as the direction of the field because a proton has a positive charge. On the other hand, a magnetic force is not going to be in the same direction as the field. In fact, it can't be in the same direction as the field. It's got to be perpendicular to the direction of the field. So, if I'm looking at this picture and it says no net force, this another way of saying this is that it's at a constant velocity. If it's not accelerating, there's no net force. Okay, in that case, then our force from magnetism would have to be just the same magnitude and in the opposite direction as the magnetic force to give us that that cancellation. So essentially here we're saying that the magnitude of FB equals the magnitude of FE, or that QVB or equals QE, and then because they have the same charge on both sides, we would essentially get just that the speed equals the magnitude of the electric field in volts per meter, or newtons per coulomb, divided by B, the magnetic field magnitude in Tesla. And so if you take the E in good units and B in good units and take the ratio, you will get something in meters per second. Now, just trying to figure out what direction would this be pointing, you have to do a little more work, because you want V cross B to give you F. So my thumb is force, my middle finger is electric field. Okay, so thumb is force, put that to the west. Your middle finger is going to be your magnetic field. Okay, so try it out, and when I try this out, I get my thumb going to the left, my middle finger is going to the north, and then my index finger is coming out of the page. And so what that means here, because this is north, east, southwest, if you imagine yourself, that's actually going to be pointing upward. Okay, last one on these magnetic forces. You'll remember that if we have a particle that's with its velocity perpendicular to that of the magnetic field, it will cause the particle to move in a loop. And I brought the apparatus in class to show you that. In this case, we have a situation where we have an energetic electron with a speed of 20,000 kilometers per second. Woof. So very fast. So V equals 2.0, and then this would be times 10 to the fourth. But it's kilometers per second, so that's an extra 10 to the third. So overall, this would be 10 to the seventh meters per second. Now you might say, is that even possible? It turns out it is. The speed of light is around 3 times 10 to the eighth. So this is less than 1% of the speed of light. Okay, it moves perpendicular to a constant magnetic field, traveling in loops. If the loop it takes has a radius of 30 centimeters, okay, so that's 0.3 meters, what is the magnitude of the magnetic field that causes the electron to turn? Okay, so the story here is that the magnetic force is equal to ma, which is a centripetal force, so the magnitude of that a that's always perpendicular to the direction of the motion is going to be v squared over r. So I will give you this equation on the test. I have given you that on your review sheet for this situation. Okay, so this is q times v times b equals mv squared over r. And it says, what is the magnitude of the magnetic field that causes the electron to turn? Okay, so then you just have to identify, what am I going to solve here? You're going to solve for b. So divide each side by v, it takes away one of the squareds, divide each side by q, and I get mv over q r. Okay, so in this situation, now you might say, okay, I don't know what to do because I don't know what m is, I don't know what q is, I've only been given v and r. But it would be at this point that you go ahead and consult your resources. So I'm going to be giving you all of the equation sheets that you've gotten so far. On the equation sheet for test 1, I gave you a whole bunch of fundamental constants, and so you should be able to look these up, and your m would be the mass of an electron, so 9.109 times 10 to the minus 31st kilograms. V is what we gave you, so 2 times 10 to the meters per second. And then Q is also a number that we used a lot in some of the problems, but you don't have to remember it. You want to go look up that elementary charge, that 1.602 times 10 to the minus 19th coulombs. And then R you've been given. Okay, and if you put everything in good units, you will get your magnetic field in units of Tesla. Okay, so we've already broached these subjects because they're not totally independent, but we did introduce, we solved this Biot-Savart law, which we said this is kind of like Coulomb's law of electrostatics, but for magnetostatics. Just like charges cause electric fields. I'm speaking in this sort of static situation. The thing that causes magnetic fields is currents. So if you want to set up a magnetic field, what you have to do is set up some configuration of currents. So we use that Biot-Savart law to find the magnetic field of a long straight wire. We used it also to solve for a loop of wire, and that we related to this dipole model, where if you get far enough away from the loop, then you can treat this magnetic moment. This is you can find the direction of that with your right hand by looping around. This has units of I is amps, so amps. Area is meters squared, amps times meters squared. And then at some distance above that loop, if you're far enough away, you can treat this just like a sort of like a point. The size of the loop is not that significant anymore. What matters is just this magnetic dipole's magnitude, and it dies off as 1 over z cubed. We also developed Ampere's law, which gave us some tools for solving for the magnetic field around a loop in terms of the current that was enclosed inside of that loop. So we did a loop integral, and that allowed us to solve for a couple of different situations, the solenoid and the toroid. I am not going to give you any problems on the test that require you to use Ampere's law. I will give you problems that require you to use the magnetic dipole model, that you require you to use the magnetic field of a long straight wire, and I would also expect to see the solenoid on your test. Just a sec. I'm gonna pause, then start again. All right, you missed some footage of me drinking the rest of my coffee. Okay, so let's go ahead and make sure that we are comfortable applying these ideas. Okay, so in lab we have used our solenoid model a couple of times, so I will expect you to be comfortable with that. So a problem that we did in class was if we have a solenoid with a length of 0.250, and a radius of 0.2 meters. So this is the inner radius. Is comprised of 120 turns of wire. Determine the magnitude of the magnetic field at the center of the solenoid when it carries a current of 15 amps. Okay, so just two things I want to point out to you on this. One thing, you actually can figure out what direction the magnetic field is pointing inside a solenoid by wrapping your fingers around for your right hand in the direction of the current, and then your thumb will be pointing out in the direction of the field. So that's sort of like if you consider one loop of current from your magnetic dipole, now you just have a whole bunch of loops of currents that are all stacked on each other. So in this case, the magnetic field would be pointing to the right inside of that solenoid. The other thing to realize is that for the magnetic field inside of a solenoid, the area is not in the formula anywhere. The internal magnetic field is presumed to be essentially constant, all in the same direction, and it only depends on the current and the number of turns per unit length. Okay, so when you're doing this, just make sure that when you stick in your numbers, one thing is that I have usually been giving this mu naught to you as 4 pi times 10 to the minus 7th. The way it's listed to you on your formula sheet is with this 1.26 times 10 to the minus 6 henries per meter. Okay, so don't get confused about this. This is the same thing as 4 pi times 10 to the minus 7th, and I think sometimes I've given this to you in terms of Teslas times meters over amps. Same thing. Okay, So when you're sticking these numbers in, mu naught 1.26 times 10 to the minus 6th henries per meter, I guess. And then I is 15 amps. And then the thing to be careful about is that little n. If you're not careful, that looks like it's going to be just 120, but in fact, that is secretly the number of loops per unit length. So you're going to have to use this unit length, and this would be 120 over 0.250 meters. Okay? And then you can stick all the numbers in there, and you should get something around 9.1 times 10 to the minus 3 Tesla. Just to keep in mind, if you're getting some big number of Tesla, you've done something wrong, because the biggest magnetic field that's been produced by people on Earth is somewhere, below 100 Tesla. Probably. I don't even know if 50 Tesla has been achieved. I think that's already too high. Okay, the other type of model that I want you to be comfortable with is the dipole model. Here it says we've got a loop with 5 turns of wire carrying 2 amps of current, has a diameter of 3 centimeters. What is the magnetic moment of the loop, and what is the magnetic field 50 centimeters directly above the center of the loop? Okay, so if we have the magnetic dipole, we can find the magnetic dipole moment, that mu, by just using our formula. So here N would be 5 turns, and then I is the current, so that would be 2 amps. And then we're given that the circle has a diameter of 3 centimeters, so then to get the area, we can just use pi r squared. So pi times 0.015 meters, and then square that. Okay, so that is where I'm getting this 0.007 amps times meters squared. That's my dipole moment. Then the question is, what is the magnetic field 50 centimeters directly above the center of the loop? So keep in mind, you need to have Z be much larger than the dimensions of the loop, and then you can use this model. 50 is quite a bit bigger than 3, so this will probably be fine. In this case, what we would do, we would use our 4 pi times 10 to the minus 7th. I'm regressing. Teslas, meters over amps, and then we're going to use our mu, and that's just going to be my 007.007 amps times meters squared. And then down here I'm going to have 2 pi. Okay, that's nice because it cancels some. And then my z cubed. So 50 centimeters would be 0.50 meters cubed. So you're going to have to put 3 copies of that in the denominator. Okay? And that should give you the B in Tesla from this magnetic dipole model. Now, you'll remember we did a problem in this most recent homework that required you to think about the magnetic field from 2 different wires. And I regret to inform you that that is relevant to the test. How is it relevant? Well, let's say that you had X and Y, and you had your 50 amp current there at 5 meters on the X axis, and you had your 40 amp current coming out at us at 4 meters up on the Y axis. Well, just as we did before in class, you could go ahead and use your right-hand rule and find your directions for each one of those currents. So if we call this current 1 and this current 2, current 1 would provide a magnetic field component going this way, B1. You would find out the magnitude of that contribution by putting in 40 amps on the top, and then R would be 4 meters. And then for our current 2 on the x-axis, we would use our right-hand rule again, find our contribution, pointing like this. And then, if we just wanted the vector, it would sort of be b1 in the x direction and then minus b2 in the y direction would be our vector, and it would have units of Tesla. And then if we wanted to find the magnitude of that, we would have to use our Pythagorean theorem, because these two are perpendicular, and then we'd find the length of this arrow right there, and it would have a length of b1 squared plus b2 squared, and then we take the square root. And that would be our b net. Now, on the review sheet, I gave you a similar problem that I believe is also worth your attention. And so let me sketch this out. It says 2 long straight wires are parallel and carry current in opposite directions. So let me draw this like the following. Let's say that I have current 1 going out of the board, out of the page, and current 2 going into the page. Okay, so they're carrying opposite directions of current. The currents are 8 amps and 12 amps, and the wires are separated by 0.40 centimeters. So just to put that more in good units, it would be 0.004 meters, so 4 millimeters. Now, the magnetic field at a point midway between the wires is, so we're looking at this point. So the R that you're going to use in your equations is going to be half of that, 0.02 meters. And I want you to try to use your right-hand rule. Okay? I'm just going to erase this to make sure that we're not stepping on anything. Okay, now, what direction is the magnetic field contribution from wire 1 going to give us? Well, if I have my thumb pointing out of the page, and then I put my palm of my hand towards the point of interest, my fingers will point up, and so my magnetic field contribution from that 8 amp is pointing like this, B1. Okay, and the magnitude of B1 would be mu naught times I1 over 2 pi, and then that R would be 0.002. Okay, now for my magnetic field 2, I want you to point your fingers in, and then your fingers would be coming up. So surprisingly, the magnetic field is actually going to be pointing in the same way. If this were pointing out, these would actually be pointing in opposite directions. So for instance, if I looked at the magnetic field between 2 wires with the same current, it turns out they cancel right in the middle. But here, my thumb goes in, my fingers curl around, and there I have my B2. And then if we look at the magnitude of these two together, it'd be mu naught times I2 over 2 pi. That same R, it's only the same because these two happen to be the same distance. And then, because these are in the same direction, you could go ahead and add them together. If they were in opposite directions, you'd have to take their difference. So they're adding like vectors. Okay, so the magnetic field here would be mu naught times I1 over 2 pi r plus mu naught times I2 over 2 pi r. And I will let you work the rest of that out as you work through your review sheet. Okay, now the last topic that we've covered in this unit is that of magnetic induction. So we talked about magnetic flux, the dot product of the magnetic field times the area through a surface, and how a changing flux can induce a voltage. And this was very important because it helps us to understand, for instance, how a DC motor works. Okay, then we introduced the idea of inductance, which is if you take the sum of all of the different fluxes through each one of your loops and divide it by the current that each one is going through each one of the loops in your device, you get some quantity L, the inductance, and we had a model for the inductance of our solenoid, and it tells us something about how much voltage is induced going against the change. And so if you have, for instance, a loop like this, a little inductor in your circuit, when you turn on the circuit, you put a battery in there, it will resist the change in current, and so instead of just having the current turn on immediately, it's going to take some time to get up to that final current, at which time this will have stored some magnetic energy, but it will just act like a wire. However, then if you short-circuited this, took out the battery, at that point this would be holding on to some magnetic energy, and it would want to keep the current going in the same direction, and the current then would not immediately die off, but it would decay. And so we came up with an expression for the energy stored in an inductor. That's magnetic energy stored from the current squared times the inductance of the inductor times 1/2. And we also came up with this inductive time constant that tells us something about how long the current takes to rise when we apply our voltage to our RL circuit, and how long the current takes to decay. So let's just do a quick example of each one. This is a nice example. It says a wire loop of radius 12 and resistance 8.5 ohms is located in a uniform magnetic field that changes with magnitude as shown in figure 3. Vertical axis is set where this is 0.5 Tesla, and the horizontal axis is set where this is 6 seconds. So this would be 2 seconds, 4 seconds, and 6 seconds. The loop's plane is perpendicular to, let's assume that's B. What EMF is induced in the loop during the time intervals from 0 to 2, 2 to 4, and 4 to 6. Now the thing to identify here is that if the magnetic field through that loop and the orientation of the loop are not changing, the magnetic flux is not changing, and then Faraday's law says that at that time interval, the EMF, the voltage around that loop, is going to be 0. On the other hand, here, while my magnetic field is rising and falling, the change in magnetic field per unit time is going to be the same, but in opposite directions. So it's going to induce a current in one direction or the other direction, depending. And then, of course, you can go ahead and stick in the numbers where the EMF that you get is going to be, if it's just a single magnetic loop, it's going to be 1 times the delta B times the area of that loop over delta T. So in this case it would be 1 times, and then the delta B would be going from 0 to 0.5 Tesla, so this would be 0.5 Tesla, and then the area would be, if it's a loop of radius 12 centimeters, it would be pi times 0.12 meters squared, and then it would be over 2 seconds. Okay, so you would get the same voltage, but directed in opposite directions in these two different intervals. Another thing that would be fair game is, I asked questions about the magnetic field inside a solenoid. It would also be fair game to talk about the inductance of a solenoid. So I've already talked about this one in class, but in this case it says if you have solenoid B has 3 times the number of turns per unit length of solenoid A, that would lead to LB being 9 times LA because of this squared. So that type of problem is also fair game. Now in RL circuits, I know we haven't done a ton with this, but we are doing a lab with this week, so I want a little bit of this to be fair game on the test. This is what I would consider to be a good question. Okay, so I would encourage you to be able to do this type of question, and I will show you an example of a bad question next. Okay, so a good question. You've got a 150 ohm resistor, so R equals 150 ohms, and a 0.8 millihenry inductor, so L equals 0.8 times 10 to the minus 3 henries. If the initial current in the circuit is 2 amps when the switch is thrown, so that's your I naught, when the that allows the current in the circuit to decay, at what time will the current be 1 amp? Okay, so this would be your final I. So this would be an okay type of question, because what you'd have to do is select to have a rising current or a falling current, and then calculate my time constant, and then calculate my T. Okay, so your time constant you can get by doing L over R, so 0.8 times 10 to the minus 3 henries over 150 ohms. And you should recognize that henries over ohms gives you some time constant in seconds. And then the main part of the next part is to figure out, is this a rising current or a falling current? So this allows the current to decay. This is a falling current, so we're going to pick the right model. So then we'd have I equals I naught e to the minus t over tau. So if you can get that far, you're going to get most of the points on your test on this one. And then you just need to do a little bit more math to get to the end. So I over I naught equals e to the minus t over tau. Then you take the natural log of both sides. And that gives you that the natural log of I over I naught equals minus t over tau. Or you can then get your time by going ahead and saying that it's minus tau, whatever that is, times the log of I over I naught. So that would be 1 amp over 2 amps. Okay, and so this doesn't have any units, and then your tau has units of seconds, so your final answer should have units of seconds. So that is a good question. A bad question using RL circuits is the last one that I gave you on your homework this week, and I know this one is tricky, so let's talk about it a little bit more. So it says at t equals 0, a battery is connected to a series arrangement of a resistor and an inductor. Okay, recognize that is an RL circuit. If the inductive time constant is 37 milliseconds, so it's going to be 37 times 10 to the minus 3 seconds. Okay. At what time is the rate at which energy is dissipated in the resistor equal to the rate at which energy is stored in the inductor's magnetic field? Okay, so this is a little tough because we're given the energy stored in an inductor. We would have to realize this is for a rising current. So it's where we've added a voltage in, not taken a battery out. So we're going to have to use our rising current. And essentially what we're going to say is, at what point is the power dissipated in the resistor equal to the change in energy per unit time? So if U stored in an inductor is 1/2 Li squared, the time derivative of that, how much energy is being added per unit time, would be, I would have to take the time derivative of this side, which would essentially be du di dt. Okay, so I'm using my chain rule there, and so this dub dt, I would have to write this as L times I, so that's my derivative with respect to I, times di dt. Whoops. So if my UB is going to be L times I di dt, and I know that, sorry, this is how much magnetic field energy is being added to my inductor per unit time, and the power being used by my resistor. So this is for my inductor, and the power being used by my resistor is I times V. So because V equals IR, I could also write this as P equals I times V, which is just going to be I times R. So my P would be equal to I squared R. So here I would have this equal to I squared times R. And the problem is asking, when do these two equal each other? So you're asking, when does Li di dt equal I squared times R? Okay, I can do a little bit of math that might help me on this. I would have L over R, I'm going to divide both sides by R, equals, and I'm going to keep my di dt here, and then I'm going to divide both sides by I, so this is going to divide that one out. I squared divided by I would just be I. Okay, so this I could rewrite as just tau times di dt equals I. Okay, now if I go ahead and continue on with this, I would need to use my model for I. So if we go back, we can see that for rising current, I has this particular form. So I has the form of the voltage divided by the resistance, and then 1 minus e to the minus t over tau. And then if I take the derivative of that with respect to time, well, I might want to rewrite this. I'm going to write this as epsilon over r minus epsilon over r times e to the minus t over tau. Okay, so that's my I, and if I take di dt, e over r is not changing in time, so the derivative of that with respect to time is 0. And then if I took the derivative of this thing with respect to time, it would be minus, and then I'd have my minus e over r, and then I'd have to take down my minus 1 over tau times e to the minus t over tau. Okay, so because I have a minus, this is just going to be plus And so now I can put this all together. Okay, I'm going to put that expression, these expressions in for my I. So I'm going to get t times di dt. So t times e over r times 1 over t times e to the minus t over tau equals I. So this would give me e over r times 1 minus e to the minus t over tau. Okay, so right now things are going to start canceling out. And notice that I can divide each side by e over r, and those sides cancel out. Here my t's cancel out, my tau's cancel out. And so I'm going to get e to the minus t over tau equals 1 minus e to the minus t over tau. And so I can add e to the minus t over tau to both sides, and I get 2 times e to the minus t over, t over tau equals 1, or e to the minus t over tau equals 1/2. And then if I take the natural log of both sides, so natural log of 1/2, I get minus t over tau equals log of 1/2, or my tau equals, the time at which this happens then is going to be minus tau times log of 1/2. Okay, so then I just have to put in my tau, which is 37 times 10 to the minus 3rd seconds, and then put in my log of 1/2, and I should get to my answer, which is 0.026 seconds. Okay, so that's a bad question because it's got a lot of work in it, and not a lot of, you don't get a lot of insight from it. I'm just putting it in there because I had a question about it from a student. So, don't worry about that. Do worry about these different topics. And I would highly recommend going ahead and doing your review sheet and trying to see how well you can do on those questions. Try to make sure you understand each one. And if you can, then you should be in good shape for the test on Friday. Okay, so good luck, and thank you for watching.